Alright, welcome to another installment of this uh, end of the year stream. I'm just about to go ahead and restore the coefficients code again. Yeah, I have no idea what's going on with Git. It is officially screwing me as usual, and I'm going to ignore it. Just hope those commits are in this repository somewhere and I can piece them back together later. Alright, so first things first, I need to fix these LUs into LLUs again, which is going to totally screw Git up yet again, and I'm going to have to go and do all kinds of craziness. Maybe what I need is to do git branch. This is the coefficients branch now, and git okay. Now go down to the delta x region and tell it to if delta x equals 0 and delta y equals 0, then continue. No. No. Git, stop screwing me. Uh, God damn it. How does this thing work? I don't understand. Why am I not committing onto the coefficients branch? What branch is that on? Why is that all on the same branch? I don't understand. Okay, um, git undo commit. Alright, I'm going to undo this. Let's see if that works. Alright. One new command prompt. To code git log. Alright, awesome. That appears to have gotten rid of the last commit. Now what I want to do is look at my git status. Brilliant. Not sure why that's red. Git branch head detached at BA05. Yeah. So let me do this again. Now let me ask, did that remove another one? Hey. There we go. Now what's my git status like? It's still the same. Ah, god damn it. Okay. Blah. Git commit. Git. Let's just get all. Keep everything, please. Alright, whatever. And now git checkout master. Git branch. No idea how git works. 2E4409. Now, give me a git log and tell me what I've got. Awesome. I've got the feasible states method. That's what I want. Okay. So, just so everything is clear to me, feasible states. Awesome. Great. Now, I'm guessing that the LU change is still broken? Yes. Yes, it is. Okay. So now I have no idea what does and doesn't work in the code because Git. So, yeah. It's going to take a little while to get all this shit figured out again. In the meantime, place all LUs with LLUs, please. Do 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 do. Very good. Delta X. And again. Let me remind you. And then do I have a coexist check timer around here? No coexist checkers. Okay. That's fine. Whatever. If delta X equals 0 and delta Y equals 0, then continue. Okay. Gonna get rid of these because I don't know if they're relevant anymore. And I'm going to ask, what is up with the Git branch situation? I'm on master, I have no idea how Git works, and I have coefficients. Okay. I'm going to now delete coefficients and no idea how Git works because I've got all the code I need here, and those other things are just nonsense sitting around that I don't know how to do anything with. So, git delete branch. Alright, there we go. Git branch minus capital D coefficients. Git branch minus D, no idea how Git works. Git branch. Great. Awesome. So now the master is sitting on the currently built version. I'm going to now ask Git how to start a branch from an old commit. I see. So, pull this up over here again. Okay, these hashes are the same, I guess. So I'll keep those sitting around. And there we go. That's what I want. Okay. Now, having screwed with Git for far too long, I guess what I want to do is git branch coefficients BA052D5A67. That doesn't seem right. That should be the coefficients branch, right? Y-fly. Yeah, back that up. That seems wrong. WC2 code. Git log. Old style coefficients. Yeah, that's what I thought. That's what I remember it saying before. Alright, so you. No, you. You're gone. Just go away. Now, you 7C0A1DEEEE. I'm on master and I have a coefficients branch. Great. Now I'd like to check out coefficients. Okay, before I do that, git status. I have no idea what that change is. Git commit -m fixes. Oh wait, git all fixes to the timer and the delta x delta y loop. Now I'd like to check out coefficients, and I'd like to make the same changes again. If delta x equals 0 and delta y equals 0, then continue. And if I pop up there to the spot where all the LU stuff happens, yep. Doopy-doopy-doo, LU with LLU. Okay, now I'd like to run. See if I get reasonable results. It looks like I did. So I'd like to commit that. Right, so I think what I need to do is get all fixed the timer and the delta x delta y short circuit. And that's on the coefficients branch now, right? And just to be sure that I'm doing everything correctly, I would like to go back and see coefficients everywhere. Yes, great. Okay, finally, this is all saying while it's less than 1, but I want it to say while it's less than 10. Build that again, run it. Now I can finally get maybe some accurate measurements here. Alright, so coefficients. Now everything from there to there gets deleted because it's an invalid run, but everything else is good. These are all making actual sense now. Single change. Awesome. Now, if I compare that to what happens when I check out master, the system is so stupid. Why would checkout be simultaneously the thing you use to update a particular file and to change the whole system onto a different branch? Like, there should be a separation between the commands you use to edit the working set of files and the commands you use to edit the state of the repository that's internal to the repository. That's very weird to me. Like, these two checkouts have completely different meanings. It's very stupid. Okay. Now I want to make sure delta x equals, yeah, this has the short circuit and the LLU, right? Great. Run that again. This time we're using the feasible states method, which we have been trying to figure out if that's faster or not, and maybe we'll finally get an answer. Seemed like it was faster at one point, but then it turned out that the way I was printing the times was wrong. So here we go. Generator runtime. 29, 32, 36, 27, 32, 39, 33, 33, 32. Versus feasible states, we get 30, 33, 30, 28, 28, 27, 29, 25, 31, 29. It's a little faster. Now, I'm curious about why it's faster. What are the counts like in these? So 8,000, 8,000, 9,000, 7,000, 9,000, 10,000, 9,000, 9,000, 8,000, 9,000, 10,000, 9,000, 9,000, 9,000, 8,000, 9,000, 9,000, 10,000, 9,000. It's a little bit higher on the second one, possibly the same. Overall, is single change generator runtime. The average lower than average. $348, 375, 356, 353, 337, 354, 345, 350, 344, and this we have 308, 319, 295, 299, 303, 314, 294, 284, 301, 309. Yeah, so it did speed up the feasible states thing did in fact speed up the propagation chain, the time it takes to do a single change, basically, which is where the speed up came from for that. Okay, so that we have an answer for. I'm gonna go fill up my water. I'll be right back. All right. So let's go ahead and assume that feasible states is better, which means, well, I guess that means I should eliminate this completely now. no longer need to keep the coefficients branch around at all. Alright, so this uses feasible states, right? Yes, awesome. And it has the short circuit. Now, let's go ahead and build the deeper short circuiting system. See if we can't get any speed out of that. So, the way a deeper short circuiting system will work, hey, that's the other thing we lost, the pointer rounder. Round putter. God damn it, how did that happen? Alright, so now that's done. Let me commit that real quick. That means the other thing we're missing is this assert right here. There we go. So now, uint 8t, the problem we want to do with is the big grid. So let's see, the finished grid. Mem set the finished grid to 0. Cell count. Out finished. Okay. let's see. Thinking about ways you could do smarter stuff, but still not seeing it yet. Might see it later. Cell count. Alright, now we have this out finished thing which got set to 0. Whenever we lock down a spot, we're going to set it to 1. And then what we're going to do is, when we're looking at delta x, delta y, right, what we're going to do is we're going to say, hey, here's a question. Yeah, why is there an extra line for these? Why don't we just, you know? Okay, so now what we're going to do is we're going to say, if it's at 0, 0, skip it. If we want to start at let's see, where is, yeah, take x2, y2, and then do an iteration across that entire spot. So for uint32 sx equals x2, sx is less than x2 plus sample width plus plus sx. Sy, y2, sy, y2 sample height, sy, and sx equals sx, uint32, ox equals sx modulo output width, output height. So wrap those back around into their proper values, and then we ask the question, what's the value here at the out grid? Right, if I take the out finished grid and I have ox plus oy times output width, right? If I index that position as so, and I see that it is equal to 0, then skip spot equals 0, break. Right? Check all those spots. If any of them has a 0, then that means that particular spot is not yet nailed down, so we don't need to skip here. Okay? If we get to here and we're supposed to skip this spot, then continue. Right? Then skip this spot. Hopefully that will, as time goes on, cull out lots and lots of coexistence checks. Right? Now the only thing we have to do is actually fill the out finished grid. So we decrease the number of coexistence checks, and in exchange we increase, and I guess I don't actually have the count of the coexistence checks, do I? I'm going to have to add that back in. So single change, time counter, coexist check, coexist So here I'm just going to begin time counter coexist check, end time counter coexist check, and display time counter coexist check. And then I want to pop up to out finished, and we're just going to go ahead and ignore that for now. Build here. Am I still doing 10? Awesome. So having done all that, Coexist check. Count. Yeah, run it. Okay, so about half of the time you spend in a change happens doing coexistence checks. That's interesting. That suggests maybe the lookup table is not such a bad idea. Although, again, it is... actually, no, because it's still a very small average amount of time spent doing that. It's the sheer number of them that causes that to be such a large contributor. It's the number, not the length of time it takes to do them. But let me take that as my new sample set for, or output set for this, so that I have those counts there. Then I'm going to include a new trick here, which is the the finished output short circuit, or I'll call that the unchanged cull unchanged, or the skip unchanged rule. So, to skip unchanged deltas, we just we do this, and then we have to modify the way the grid works. So, the way that happens is after during propagation, at the beginning of propagation, we have the change queue. Change queue. I'm set on change queue. And that gives me a set of changes right here. What I want is a set of yeah, another set of changes. God damn it. Okay. So now I have this extra queue that's not infinite in size, but that can contain. No, why don't I do both of these this way? Because this would work for this too. Changes. Clear changes to 0. Cell count. because then we can assert that we have enough memory for the change queue as well. And then what I want to do is when I'm propagating, doopy-doopy-doo, we come through here, we pull a change out of the change queue, and what I would like to do is out the other end, once I've pulled something off the change queue, well, let's do it up here, right? I'd like to take the changed to completion thing. By the way, let's pull all the cell 1 stuff out here because it's kind of dumb to do that work multiple times. Right, so there we go. Now if here's the idea. If cell 1 base equals 1, that means that there is only one viable state for that cell. That means it's completed. So what we then do is we ask, has this cell been set to be fixed before? And in order to do that, I'm not sure how we'll do that. Well, let's deal with that later. We're going to put this onto the changed to completion queue by going changed to completion or completion count plus plus, and just put the change right there. Okay, so then when we're done propagating, what we'll do is we'll say, okay, begin time counter update out grid end time counter, and for that all I do is go across everything in the completion array, and then for x to y, w to h, get the actual x position we care about, like so. And then finally set the out finished OX plus OY times output width to 1. And then once all of that is done, take the completion count, set that to 0. Now, the only thing left to do is make sure that make sure that the a particular position never gets pushed on there twice. Now, there's a couple ways I could do that. I have this on change Q array. Now, on change Q gets cleared to 0 when I first take it, but after that, it stays clean. And the only way I ever interact with it is either wave2d add change or by setting it to 0 right there. So I feel like I could use that to store more information than what I'm currently using it for. So let's try that, right? Let's add the rule that there's an define on change Q mask, which will look like this, and on completion Q mask, which will look like this. And so, if you come in here and you look at on change Q, and you ask that mask to on change Q mask, then what you might do is you say, okay, great, change count is less than blah, change max result equals add change success, blah blah, and then or equals on change Q mask. Okay? And then if I go down to on change Q at the very bottom, that is just a matter of and on change Q mask, right? And then what we do is up here, when we go to add something to the completion queue, we go if that is equal to 1 and on change Q perfect. If that is exactly got a 0 on the completion mask, alright, gotta fix some compilation errors here. Time counter, update out grid, make time counter. Signed, unsigned mismatch, huh? Completion count. That doesn't need to be assigned. Alright, great. So, now, we clear that whole thing to 0. When we put something on the change queue, we set a bit on that array that says this particular cell is currently on the change queue. And when we take it off, we set that back to 0. When we put it on the completion queue, we set that to 1, then we never will, do we? We don't set that to 1, actually. So on completion queue. Right. So I want to take all that and say, if we add it there, then set that as being on the completion queue. And we never turn that off. There we go. Alright. See if that works. Now it's saying that this is slower, which is interesting. Not sure why it would be slower. Is that saying that it's slower? Wait, no, I'm not used to the size of these numbers. So, how slow is this thing actually? Generator runtime 88, 95, 85, 86, 81, 88, 81, 95, 87. Okay, so mid-80s to mid-90s, right? Here we have 85, 91, 79, 86, 79, 83, 87, 94, 99, 87. So that seems like a little bit better. Did that decrease the count of 3668, 3666, 465, 406? Yeah, so that successfully decreased the count. Now what I don't know is how much time are we spending on this new thing, and that's because I'm not displaying it. So please display the update outgrid. Alright, now run it. Okay, so these here should be very similar runs actually. You know what I'd like to do? I'd like to, before we compare the times, just double check a theory of mine, but I'm pretty sure that these should lead to very similar results. So I'd like to test that by saying let's run this. Well, let's just run it once. Run. Boop. Alright, so there we go. Let's think of a couple identifying features. So it has that sort of shape that it always puts in there that goes around one of the rooms. It's got this little square here. It's got a little mushroom cloud shaped thing there coming out of this pair of rooms here, which loops back around to there. Very interesting. Okay, so that is that shape. Now let me take out this whole outgrid thing entirely. Outgrid. Let's suppose we never update the outgrid. Skip spot. We never do a skip spot, and we never put things into the change queue there. Alright, so same as if we didn't have it at all. You know what, we can even go a step further. Take that out as well. Okay. Ah! Awesome. So my theory is right. These are running exactly the same simulations. And the only reason I know that these won't be different at all is that even though there's no randomness in the propagation rule, anything I do that changes the way the propagation sort of lays out those feasible state arrays changes the results. So if I change the order of the array but keep all the same values, although the probabilities all stay the same, the result you get from the same seed changes. Okay, but this doesn't actually do that at all. Even though I'm culling out checks that we were doing before, the checks I'm culling out are ones that we knew had to fail. That was the whole idea. They had to result in no new information. So that means if I compare the new stuff to the old stuff, I'm not just looking at similar things. The first run of the new thing is an identical run with just more wasted check time, right? So it's literally doing the same amount of work, and I can see an exact amount of change in the number of checks that have to be done for each one, so that I can get an idea of how much you actually save by this. Okay? So, yeah, okay, awesome. So, now let me look at the output from this versus the output of over here. The time it spends doing each thing I don't care about so much right now. What I care about is how much time trade-off there is here. So the coexist check here took 528, here it took 527, and in exchange we had to spend about 1/50th, no, 1/200th of the same amount of work. No, what is that? That's 4%. It's basically we increase 4% in this spot, but decrease by from that 8 to that 7 there, right? So down by 100. It's actually not down by 100. That's down by what? 70. Up by 4. That's good. That's good. And here there was an 8 there, so that's 87,000 over here. That dropped down to 68,000, so that's about 9,000 fewer coexistence checks that it had to do. So not huge, but not zero. Would have liked it to be bigger. The next one down, 4684. Wait, no, that's the average. The next one down that I care about, where's the count? 40697. Whoops. The next countdown that I care about over here is 4, 5. Yep, 5. 40679. So that's a nice decrease by about 20,000. 1, 2, 3, 4, 5. Oops. Um, 3856 went down to 3854 again. These are all decreasing by about 20,000 pretty regularly, which is not bad. 19,000-ish. I mean, given that there's a few million, it's not a gigantic dent, which is why the amount of time it's taking doesn't change too much, but it's something. Certainly, you're gaining something for it because this here is smaller than the amount of time we decrease by, right? Like this over here is 54765, this over here is 5426, so again, big drop in this digit, and then you have to spend a little bit more time here. Now this did take overall more time. Curious if that's just indicating that there's more important things that time is going to. Where did that 1 come from that wasn't over there? 8, 9. The difference is how much time it spent on propagation total. So even though this went down by a little bit, the total amount of time spent on propagation is actually up. Fair enough. Is that consistently true on all of these? Propagation time there is also up. Propagation time here is down. Propagation time there I think that's this one. It should have similar counts. Those are not very similar. That must be this one. 3642, 3640, off by about 20,000, so that's the right line up there. Yeah, so a nice decrease in propagation time there. So it does look like only about half of propagation time is spent in coexistence, in the literal coexistence check. There are a ton of them. But I wonder if I expand out that scope a little bit, so that it encompasses more stuff, how much closer to 100% that becomes. So here is everything that happens on a per pair of samples basis. Everything else that happens is other stuff. Well, that's not what I wanted to see. Kind of cool though. Whoop. Uh-oh. Begin time counter coexist check. Yeah, so there's still some other time that's unaccounted for. That's kind of interesting. As you can see that it's only a little over half the amount of time that it takes to propagate is actually spent doing coexistence checks. Now, if those coexistence checks could be less than 100 here, like we could decrease this whole thing by 2 digits, that would definitely decrease this down by about half, right? Because this would go from having a 500 there to having a 4 there. There's still a bunch of other stuff happening. Plus, I don't think it's very likely that this gets any smaller. Maybe a little bit smaller with the lookup table, maybe a little bit, but I'm not sure. I mean, we could try it. We could definitely try it. I'd still love to get these the number of checks down lower, but I'm not sure how else to do it yet. I have to think for a while. But maybe we can try to find more of that time. So coexist begin time counter coexist check. What else am I not measuring that goes on around here? There's all this work that happens here for setting up for a particular delta xy, so let me do that. Begin time counter delta xy pre-process. Alright. Here's where we end it. Here's another spot where we end it. And here we're done with the pre-processing. By the way, there we go. probably get rid of this self-finished array if I want, so maybe set out to do that next. Make time counter delta xy make time counter. Gotta make that shorter so it'll fit. Oops. Forgot to build it first. Alright, so here we go. Looking for where the rest of that time goes. Also frustrated that this thing doesn't update real time. It used to, but now it's busted again. Not sure why, but it's upsetting to me. Okay, so let's take a look. Yeah, so that right there is bigger than this and much smaller than this. So that pre-processing, getting it down would be nice. It also tells us how many sample pair, cell pairs we ever compare, which is kind of interesting, because now we know exactly a ratio between per change how many comparisons we actually do, which is just going to be 24, right? That should be, if I've done my math correctly this whole time. Although 6 times 4 is not 20. 6 times 4 is not end in 0, so I'm not actually sure. Duh, right, of course. It does 25 because it counts those times when we short circuit the XY. Right. So each change involves a 25-step loop. Some of them get short circuited, which is nice. But that does not count how many of them get short circuited because we are putting the counter above that. Now, on average, that spends a 312 to do all that pre-processing, which is interesting. Seems like a lot. That includes doing the skip spot testing. That probably takes a little bit of time. Doing this takes a little bit of time. Yeah. Not sure if it can be too much smaller than this. I mean, there's some minor things I can do to crank stuff up, but I'm trying to look at major things first. Yeah, okay. So that's not a major contributor. T2, T1. We look up sample 1, sample 2, we compare them. That's only half the time. Where does the rest of the time go? This doesn't look like it should take too much time. So what I'm going to do first is I want to add a quick thing here for counting how many times I do a full check, right? So if I get past here, I do a full check on that cell, and that's a nice thing to know. And then the next thing I want to do is, given that I don't know how much time it takes to I don't know how much time it takes to add something to the change queue, I want to time that as well. High PD codes, yeah, I'm going epically long so that I can make a bunch of videos. I've so far recorded 3 separate sessions here during this stream to upload over the next couple of days to finish this year strong. Alright, so I want to know add change. Okay, so add change. Right now I'm trying to figure out where all the time goes during the propagation phase, because I haven't been able to isolate it very well yet. In case anyone is joining me right now, run. All the heavy timing is slowing down. Look at this. It's telling me that just so that's a count of 206,000 times it actually did it. So that is preventing actually about 30,000 full checks. Now, some of those are probably from short circuits on the delta x equals 0, delta y equals 0 case, and the rest are the outgrid. About 20,000 probably are outgrid. Now, actually, we know exactly 9,317 of them are the short circuits, because one of those short circuits every time. Now, the fact that this takes so much time is interesting to me. That means that just the act of timing a block actually slows it down considerably when it's got such a large count, right? So this large count here means that, you know, this probably is about 80 steps bigger than it should be, which means it would only be about a 60. So the fact that this contributes half the time is kind of misleading. Although, looking at other things like add, change, and stuff, I still don't know where the rest of that time is coming from for propagation. That could be time that's being unmeasured, but is actually passing because of the counters. Yeah. Man, profiling is tricky because you can't. It's hard to profile without affecting the system. Let's try something here. Perfect. Okay, so now let me just track down a few more of these equals 4 spots. That should actually be 4 or 5s. Alright, now I have a debugging level of 5, which lets me turn off all of the excessive timing and just look at the high level times and see how much different they are. Look at that. Without all the timers, the times are down to like 28, 31, 26, 29, 26, 29, 29, 30, 32, 28. Okay, so that means what I need to do is stop using this as my major comparison system and start using this. There we go. Now this is actually one of these, and what I'd like to do is compare that to by the way, let me go ahead and get that now. Upgrade to skip unchanged deltas. Okay. Now let me go back down to outgrid, out finished. Right. Boom, 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 boom. Change to completion. Boom, 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 boom. Alright, so now this is running without this skip unchanged deltas code, and I'd like to see how much I actually gain or don't gain from it. Alright, so that's interesting. This is looking like a low of 27, which is pretty common, but all the way up to 34, and there's a 31, 30, 31 in there, and 29's a lot. Here I'm getting a similar low of 27 and a high of 30. Not convincingly that much difference. I mean, the number of 27s that happen here is 2. The number that happens here is 2. Oh, there's a 32 there. So not quite a 34, but pretty much the same. It looks like if you go step by step all the way through it, it's almost lower on every single one of them. These two are not lower than the ones they pair with, and neither is this one. So more of these are lower than their pairs than these. I guess I could roll the die one more time and see if we still get similar results. F87305E. So let's see. This one on the left is actually smaller than its pair there. And that one's bigger. That one's smaller. That one's smaller. That one's bigger. That one's smaller. Yeah, it looks like it's mostly a wash. You don't see a huge, obvious improvement because of it. Which means that the right thing to do is to get rid of that code, because it's just not doing that much for us that's perceptible right now, and it's complicated. So here we go. Update outgrid, gone. Skip spot, gone. Update outgrid, gone. There we go. Alright. And we can get rid of those masks too. Okay. Let's see. I'm going to take a quick moment to start one last video here. This will be the last one. I'll be right back.